Voyager 2's leaky hull discovery at the edge of the solar system. In November of 2019, 5 separate teams of scientists published their findings together in the journal Nature Astronomy, all analyzing data from the same historic event. Voyager 2's crossing into interstellar space almost exactly a year earlier. Buried inside that coordinated release was a detail that quietly complicated everything Voyager 1 had already taught scientists about the edge of our solar system. Picture 2 spacecraft, launched within weeks of each other back in 1977, sent on completely different trajectories through the outer planets, finally arriving at the true edge of the solar system years apart. Only to that, the boundary itself didn't look the same from either vantage point. The 2 spacecraft hadn't found the same kind of crack in the same place. They'd found 2 different kinds of leaks, running in opposite directions, at 2 completely different points along the same protective boundary. This is the story of what Voyager 2 confirmed about the crack in our solar system's shield, why it leaked in exactly the opposite direction from what its twin had already shown scientists years earlier, and what that difference reveals about a boundary far stranger and more complicated than anyone expected, before 2 spacecraft actually managed to sample it twice. To understand why Voyager 2's discovery mattered so much, you first need to know what Voyager 1 had already established about this same boundary 6 years earlier, when Voyager 1 approached the Heliopause, the outer edge of the Sun's protective magnetic bubble, back in 2012. Its instruments spent roughly 28 days threading through a genuinely turbulent transition zone before finally, fully crossing over, a full month of ambiguous, back-and-forth readings, rather than any single, clean moment anyone could point to and call the crossing itself. During that extended approach, project scientist Ed and his team documented something unexpected on at least 2 separate occasions. Before Voyager 1 had technically left the Heliosphere at all, the spacecraft found itself directly connected to the interstellar environment outside, material from beyond the solar system's boundary reaching inward and briefly touching the spacecraft before it had even officially crossed the threshold. Researchers described the region Voyager 1. Voyager 1 crossed as riddled with tendrils of interstellar particles that had already punched into the heliosphere's edge, like tree roots, slowly working their way through solid rock well ahead of any dramatic breaking point, invisible fingers of outside. Material already threaded through the supposedly sealed wall protecting the entire solar system, long before anyone officially declared that wall breached. Voyager 2 told an almost completely opposite story, and the contrast started with simple timing. Where Voyager 1 needed nearly a month to fully complete its transition, Voyager 2 made what scientists have since described as an unexpectedly clean break, crossing the Heliopause in less than a single day, its instruments registering a sharp, almost surgical change, rather than the drawn-out, back-and-forth ambiguity that had defined its twin's crossing years earlier. On the surface, that sounds like a simpler, more straightforward event than what its twin experienced. The kind of tidy, well-defined boundary crossing scientists had originally expected both spacecraft to encounter before either of them actually got there. What came next revealed it was anything but simple. Even after Voyager 2's instruments confirmed the spacecraft had genuinely crossed into interstellar space, its low-energy charged particle detector kept registering something that shouldn't have been there anymore. Particles that had originated from inside the heliosphere, from the sun's own solar wind, continuing to show up in the data well after the spacecraft was already supposed to be outside the bubble entirely. Ghost signals from a region the spacecraft had, by every other measure, already left for good. Ed Stone summarized the contrast between the 2 crossings about as plainly as they ever state something for the public record. On Voyager 1, he explained, the team found that even before they'd left the heliosphere, they'd experienced 2 separate episodes of being connected to the outside, material from beyond the boundary reaching it ahead of. On Voyager 2, the situation was reversed entirely. The spacecraft was outside, fully confirmed to have crossed, and it kept detecting particles leaking from the inside anyway. Solar material somehow still reaching a spacecraft that had already, by every other measure, left the sun's bubble behind. NASA's own description of the discovery leaned into a metaphor simple enough to capture exactly what this meant. If the heliosphere is like a ship sailing through space, its hull turned out to be somewhat leaky, and the leaks ran in both directions, depending on exactly where along that hull you happened to be standing when you checked. Voyager 1's leak let the outside world seep in ahead of schedule. Voyager 2's leak let the inside world keep seeping out long after it should have been sealed off. Completely. 2 spacecraft, 2 different locations along the same boundary, 2 completely different failure modes in what was supposed to be a single, continuous protective barrier. That difference in behavior traces back to a difference in geography, and it's worth picturing exactly where each spacecraft actually crossed. As the entire solar system moves through the galaxy at roughly 450,000 miles per hour, the heliosphere doesn't sit still either. It gets shaped by that motion, the same way water piles up in front of a moving boat and trails out behind it in a wake, compressed and pushed on the leading side, stretched and drawn out on the trailing side. Voyager 1 exited close to the very front of that structure, the leading edge directly facing the direction of the solar system's motion through the surrounding interstellar medium, essentially the bow of that metaphorical ship, the section of hull taking the most direct head-on pressure from the oncoming interstellar wind. Voyager 2, crossing at a completely different point 6. Years later, exited instead along the heliosphere's flank, more like the side of the hull rather than its leading point, a region experiencing entirely different physical stresses and interactions with the surrounding interstellar medium than the bow ever would. And according to the research teams studying both crossings, that flank position appears to be measurably more porous than the region where Voyager 1 crossed. An entirely different section of the same boundary behaving according to its own distinct rules, shaped by its own distinct local physics, rather than any single universal formula applying equally everywhere around the bubble's entire surface. One of the researchers involved explained why having both datasets mattered so much, in terms that get right to the heart of why a single spacecraft's data, however impressive, was never going to be enough on its own. Without Voyager 2's new measurements, there would have been no way to know whether what Voyager 1 experienced was genuinely characteristic of the entire heliosphere, a universal rule describing the whole boundary, or whether it was simply a quirk specific to the exact location and moment when Voyager 1 happened to cross. With two independent data points now in hand, from two different locations, years apart, scientists finally had enough information to recognize that the boundary itself isn't uniform at all. It behaves differently depending on exactly where along its surface you happen to be sampling it, a genuinely important structural insight that a single spacecraft, no matter how good its instruments, could never have revealed on its own. The leaking particles weren't the only place Voyager 2 either confirmed or complicated what its twin had already found. Its magnetic field instrument delivered its own independent verification of one of Voyager 1's strangest results. The direction of the magnetic field just beyond the Heliopause turned out to be roughly parallel to the magnetic field, measured just inside it, rather than showing the sharp directional shift that standard models had predicted should mark the true boundary between the Sun's magnetic domain and the wider galaxies, a boundary that, according to decades of pre-Voyager theory, should have looked as distinct as flipping a switch, one clear magnetic orientation abruptly giving way to a completely different one the instant, Scientists had genuine reason to wonder whether Voyager 1's version of that finding might have been some kind of coincidence, a fluke tied to its own specific crossing location, an anomaly that a wider survey of the boundary might eventually reveal to be a one-off rather than a genuine, consistent feature. Getting the same basic result from Voyager 2, crossing at an entirely different point on the heliosphere's surface, years apart and under completely different solar conditions, made that explanation considerably harder to... A result that shows up once might be chance. The same result showing up twice, two independent spacecraft sampling two different locations, starts looking like a genuine unexplained feature of how this boundary actually works, one that, as of the most recent mission updates, still doesn't have a fully agreed upon explanation, sitting on the growing list of heliophysics puzzles that both spacecraft have left behind for the next generation of researchers and instruments to eventually resolve. There's a third puzzle buried in the comparison between the two crossings, and it's arguably the strangest one of all once you sit with the numbers. Voyager 1 spent an extended period moving through what researchers called a stagnant layer of slowed, thickened solar wind before finally crossing over, a transition zone with a measurable width. Voyager 2, crossing along a completely different section of the boundary, at a different point in the Sun's roughly 11-year activity cycle, encountered its own version of that layer as well, given how different the two crossing conditions were, different locations, different solar activity levels, different structural regions of the heliosphere entirely. Researchers genuinely expected those transition layers to differ meaningfully in size. Instead, the two layers came out nearly the same width. Patrick Coyne, a heliophysicist involved in analyzing the results, described that outcome about as bluntly as scientists tend to describe something that doesn't fit their working assumptions, calling it very, very weird, and noting plainly that the field needs considerably more data before anyone can properly explain why two such differently positioned, differently timed crossings ended up producing such strikingly similar measurements. It's worth being honest about how much this entire comparison still leaves unresolved, because that honesty is part of what makes it credible rather than sensational. Voyager 1 exited near the heliosphere's leading edge. Voyager 2 exited along its flank. Between those two single points, sampled years apart, scientists have gathered exactly two data. Points describing a three-dimensional structure that extends in every direction around the entire solar system, including regions neither spacecraft has ever come close to reaching. Nobody has any direct measurements at all from the heliosphere's trailing wake, the region analogous to the water trailing behind a moving boat, a section of the boundary that current models suggest could stretch out considerably farther than the more compressed leading-edge Voyager 1 sampled, meaning the overall shape of the U. Structure protecting our entire solar system remains, in a very real sense, still fundamentally unmapped beyond these two narrow slices of data. Everything scientists currently believe about the heliosphere's true, complete shape is built from extrapolating outward from exactly 2 points on an enormous three-dimensional surface, an approach roughly equivalent to trying to describe the entire coastline of a continent after only ever having stood on two separate beaches, one facing the open ocean, the other tucked along a sheltered inlet, with everything in between left to educated guesswork rather than direct measurement. That incompleteness carries real, practical weight, because the heliosphere isn't just a scientific curiosity. It functions as an active shield, deflecting a meaningful portion of the dangerous, high-energy cosmic radiation that constantly streams in from elsewhere in the galaxy, radiation produced by supernovae and other violent events scattered across the Milky Way, radiation that would otherwise reach Earth and the rest of the inner solar system in higher concentrations. If the boundary leaks differently, depending on whether you're standing at its front, its flank, or somewhere along its unmapped trailing wake, then the shield's actual effectiveness likely varies considerably more across its full surface than a simple uniform model would ever predict. The astronomical equivalent of discovering that a supposedly watertight roof actually lets rain through at different rates depending on which section of shingles you happen to be standing under. Understanding exactly how and where those leaks occur, and how consistently they behave over time, matters directly for any future effort to model radiation exposure for spacecraft, or eventually human missions, that might need to operate anywhere near this outer boundary in the decades ahead, long after both Voyagers have gone silent, and any future mission is left working purely from the data these two aging spacecraft managed to leave behind. There's also a quieter, more human dimension to how this particular discovery came. Together, that's worth appreciating on its own terms. 5 separate research teams, each focused on a different instrument's data, coordinated their findings and published them together, in the same issue of the same journal, specifically so the full, combined picture could be understood all at once, rather than trickling out piecemeal across separate papers that might never get read side by side. That kind of coordinated, comprehensive release is itself a recognition of how genuinely complicated this particular story had become, complex enough that no single instrument's data, taken in isolation, could tell the full story on its own. It took particle detectors, magnetometers, and plasma instruments, cross-referenced against each other and against Voyager 1's earlier results, before researchers could confidently start describing what this crossing actually revealed about the true structure of the boundary protecting our entire solar system. So here's where that leaves things today. The crack Voyager 2 confirmed at the edge of our solar system isn't the same crack its twin found 6 years earlier. It runs in the opposite direction. Solar wind material leaking outward into interstellar space rather than interstellar material leaking inward, situated along an entirely different section of the heliosphere's surface and accompanied by its own set of genuinely unresolved puzzles, an unexplained parallel magnetic field, and a transition layer's width that matched its predecessors far more closely than anyone studying the data actually expected it to. Think about what it actually means that humanity's entire direct understanding of this boundary rests on exactly 2 crossings, sampled years apart, at 2 specific points along an enormous three-dimensional surface. Every model of the heliosphere's overall shape, every prediction about how effectively it shields the inner solar system from galactic radiation, every textbook diagram showing a tidy, comet-shaped bubble surrounding the sun, is built by extrapolating outward from those same 2s. Narrow slices of real data filling in the rest with physics-based simulations that remain, by definition, untested against anything Voyager 1 or Voyager 2 actually measured directly. That's not a criticism of the science. It's simply an honest accounting of how little of this boundary has actually been sampled firsthand, and how much of what gets presented confidently in documentaries and textbooks is still, at its core, an informed extrapolation rather than a direct measurement. 2 spacecraft, launched within weeks of each other in 1977, aimed at completely different trajectories through the outer solar system, ended up providing humanity's only 2 direct samples of a structure that extends, unmapped and unmeasured everywhere else, around the entirety of the solar system we call home. Whatever else that boundary is doing at its unexplored wake, along stretches of its surface neither spacecraft has ever come close to reaching, remains for now one of the largest genuinely unanswered questions left in our own cosmic backyard. Waiting for some future mission, launched by people not yet born, using instruments not yet designed to finally go check for itself, decades or perhaps centuries after the last signal from either aging Voyager finally goes quiet for good.